My name is Cory Isaacson. I'm the CEO and CTO of CodeFutures. We make DB shards for database scalability and sharding. I also wrote a book called Software Pipelines. If any of you are interested in scalability architectures, it's kind of an interesting view on that, I think. But the main thing I wanted to talk to you today about is how you can really scale your database in the cloud. That's, of course, the whole subject, right? And there's a lot of different kinds of databases I know that we're all using. I bet that there's nobody here that actually really likes having slow performance in their database. Anybody vote for that? I don't think so. One thing we know is that, have you ever had database be the bottleneck for your application? Anybody seen that problem? Right. And it's no fun when that happens, is it? It's, I think that's the worst experience as a DBA or an application developer you can run into, especially if it's in a production application and you really have to get the whole thing up and running and you're under some time crunch and other things like that. So nobody wants to see that with their users and applications set up. And it's especially challenging in the cloud. I actually think it's much harder to get your databases to perform well in the cloud than any other environment I know of. I have been working with databases for a long time. I used to run a company called Rogue Wave Software. Earlier than that, I've been in the field about something like 25 years, and we worked with really every kind of database you can imagine. We were early Sybase adopters back when Sybase was before actual SQL Server and Microsoft. So we really have seen the entire history of database technology for a very, very long time. And so we based all of our technology and everything we're going to talk about on that experience. The objective today is to give you actual useful information that you can really take back and use. We're not going to be talking about product-specific things at all. It's really the idea of how you can apply this and hopefully get something that will help your application run. I am going to be telling some customer stories. One of those stories is from a company called Family Builder, and we happen to have David Blinder, the CTO of Family Builder, here today. So if I say anything wrong, he'll correct me, but hopefully we'll have it all correct. So the challenges in cloud computing is that everybody likes the flexibility of cloud computing. It makes system administration much, much easier. You can get servers up and running very, very easily. It's very flexible. It scales with need. That's really the whole reason to go to cloud computing. Rightscale in particular makes that very, very easy to do. And I know if any of you have been around Rightscale for very long, you know that they have an expression called no hype, right? So we don't want to talk about any hype today. We want to talk about what it really actually takes to make an application really work and perform in the cloud from the database perspective. It's pay-as-you-go model. You don't need a fixed IT staff. However, how many people use the cloud today? Public clouds. Okay. Anybody ever seen a failure? It's kind of a joke, right? A couple of weeks ago, I think we all saw one, right? A few weeks back, right? It was pretty brutal. So what we know is that cloud services occasionally fail, right? You can have disk infrastructures go out. We see a lot of network infrastructures, and just in our customer base, we probably see a cloud failure once every week or two, which I think is way too high. And I noticed that actually, in all honesty, it's getting better. We're seeing them less frequently than we did before, but they still happen more than when you like. And when it hits your database, it's really, really difficult. And that's a very important thing that we'll be talking about. But again, cloud services are by their nature transient, so how do you work around that for database data? And that's what we're going to be talking about. The other thing, though, that makes it challenging is that resources are constrained in the cloud. You don't have anywhere near the CPU, memory, disk I/O speeds in the cloud that you're used to in a physical data center. Even if you're doing an outsourced data center, you typically have much, much better infrastructure resources, much, much more under your own control. In the cloud, you can be part of a rack that's got many, many servers in it that are sharing a lot of services between you and who knows who else. And so you're competing for all of that, and it really can be a big, big problem. And with database performance in particular, it's very, very noticeable when that happens. We actually have seen that we can have about 5 times faster I/O rates on physical hardware than on the cloud. So it's not a small difference, right? It's a very, very big difference. And if you don't plan for that, you're really going to have a lot of trouble. And we actually call this the cloud I/O barrier. That's actually something that David helped us coin, but it's something that's been very, very significant. So it's important to understand where the database fits in the architecture. Essentially, a typical application these days that we see in the cloud looks something like this. We have the load balancer tier. We do that for front-end distribution. We then have application servers, so those could be whatever kind of application server you're using. You could be using PHP application servers. We see a lot of Python and Django these days. We have Java, all kinds of things. And then on the back you have the database tier. Typically, most people running a typical master-slave type architecture where you're doing asynchronous replication, from one database to the next. So when you look at each of these tiers, it's important to understand when you're scaling what you want to do to make the performance go better in each individual tier. So now scaling the load balancers is a piece of cake. Why? Because load balancers are stateless. There's really nothing that you're storing there. If something goes down, you can just add another one. You can have redundant load balancers very, very easily. Again, if one fails, no big deal. You just bring up another one, or hopefully you already had another one running. So we're really not worried about that. The application servers are usually very easy too. Most often, application servers today are stateless. They don't have anything in them. So again, you can have 4, 8, 16 application servers. If one goes down, no problem, you just fail over to another one, especially if your load balancer infrastructure is good. Now, some of you may be storing sessions, though, in the application server. And if you do, you'll lose those sessions. But the worst case that happens is if a user loses a session, they can log back in and get another one. It's really not so bad. There are ways to replicate sessions. That's not so easy to do in the cloud, but it can be done if you really have to have that type of seamless work across. But again, generally, it's not too critical if one of those app servers actually crashes. But scaling the database tier is anything but easy. It's hard. And for anybody here actually tried to scale their database before? Okay, some a little bit. All right. Databases, of course, are stateful by definition. That's what they do, is they store information. If we lose the information and we don't have it, then they're not really a database, are they? So that's very, very critical. We also have large integrated data sets. One thing we know is that databases never get smaller. I've seen this throughout my entire career. Databases only get bigger, they only get more complicated, they only get used harder. That's always the case. And I don't care what type of database you're using, that's what happens. So we're seeing people running anywhere from tens of gigabytes all the way up to terabytes and more. And to manage that, you really have to be able to, again, keep your infrastructure alive no matter what. They're also I/O dependent. That's a very, very critical thing of databases, is they're I/O dependent. And even if you're running an in-memory database, generally you have to have some sort of way to either back it up or restore it or log transactions on disk, and so you're going to be hitting disk I/O barriers. That's pretty axiomatic for any type of database. Again, if you remember, we talked about the fact that the I/O on the cloud is a lot slower. It's also not as predictable. You can see I/O rates go up and down throughout the day. So what do you do when that happens? And that dramatically affects your performance. And if you have a disk-based database like MySQL or Postgres or SQL Server or DB2, any of those, they're all going to be dramatically affected by that. But again, even a lot of the NoSQL databases are heavily disk dependent as well, and you can run into the same type of problems. So, and of course, if a database goes down, I don't wish that on anybody, right? That can be your worst nightmare. We've seen many, many customers have databases go down before they use us, of course, but they do go down. And when it happens, the recovery time can be significant. There were some pretty famous, I think late last year or early this year, some pretty famous outages that had to do with databases where some, very popular names were down for days. So it really can be a huge outage as far as what it actually causes to an application. So you don't want to have that happen. The other thing too is if you have a big database, to do anything with it takes time. Has anybody ever had a problem re-indexing their database or optimizing indexes? Right. So we have customers literally who haven't been able to do that in years because they're afraid to do it, right? Because it would take the application down too long. So it's a very significant thing. But if you can't optimize indexes, what happens? The database gets slower and slower. You're making the I/O problem even worse. Take that and combine that with slower cloud I/O, and you've got a real mess on your hands. So databases really form what I call the last mile of application scalability. Again, you really have to be able to address this if you want to be able to scale. So the first thing we always recommend, and I suggest this to anybody here, is the first thing you should do is just optimize the database as it is. Very often with some query optimization, performance tuning, things like that, you can get things to run a lot better in a very, very short amount of time with no risk. That's a very, very easy thing to do. But what you need to do beyond that is you have to implement a real follow-on scalability strategy, because I would bet that everybody here has an application that is either growing fast or you want it to grow fast. And either way, you need to be prepared for that. And again, it's not a simple thing to do, but you need to be able to have a strategy to do that. So we talked about the cloud I/O barrier, so now I'm going to tell a little bit of the Family Builder story. You can't see the colors too well because the projector is a little off, but this is a Rightscale CPU graph, and what you're seeing in what looks brown is really red. So if you can imagine that's red, we'll be in good shape. But basically we have an expression that comes back all the way from the mainframe days, which is that all CPUs wait at the same speed. That's what they do, right? So they sit there and they get slow, and what's happening here is, in this particular example with Family Builder, when we started with them, their I/O wait was out the roof. So the CPUs were waiting for disk I/O and not being able to perform actual user requests. You can see the blue, the little bit of blue on the bottom was the only actual productive usage of CPU. The rest was just sitting there, waiting for the disk I/O to catch up. So it was a huge bottleneck in their application. And Family Builder is an application that was actually one of the very, very first Facebook applications ever. I think they were in the first 500, if you can imagine, Facebook applications in 2007. They started in a data center. That wouldn't scale. They moved to the cloud with Amazon and Rightscale. They implemented there. And one of the first things that happened was that they would actually they did marketing in the very first day, and they basically got, I think, something like 25 or 30,000 users that day, and the thing crashed because they had this kind of problem. It was just very, very quick. So the way David told me the story is he says he ran down the hall to the marketing people and said, "Don't do any more marketing until I fix this. So just to stop it," right? And so he did that, and he came in the next day, and guess what? 40,000 people came. And he said, "I told you not to do marketing." But what happened? It's a social networking application, and it was growing virally, and it was really out of control. They couldn't do anything about it. So this is the kind of problem that they had, and they adjusted and adjusted and adjusted by optimizing the database and doing more things and fixing their queries, really for probably 1 or 2 years before they actually started working with us. We'll show you the after picture soon, but anyway, it looks a lot better after this. So what are other things that actually add to these challenges with scaling your database? One is databases have to be ACID compliant. So you have to have consistency, you have to manage user contention. How many of you have multiple users and you can't afford to have conflicts between users with your database? Pretty easy guess, right? You can't afford to have that occur. You also have operational challenges, again, failover. Everybody's worried about disaster failures, so we all know that that's a big concern. But what about just routine maintenance? We were talking about this. You could have an application that could take a database that could take days to optimize. It's entirely possible when it gets too big that it requires that much time. So how do you actually do the planned failover so that you can actually manage all of that? And this comes a lot from maintenance because of indexes. And it doesn't really matter what kind of database. I know there's a lot of interest. How many of you are either using or want to use NoSQL databases? Great. Okay, and the rest are using relational? Yeah? Okay, good. Mostly relational. Well, they all have the same problem, and these technologies over time, I think, are going to merge and get more and more similar. But basically, the biggest bottleneck you have in a database, especially when it comes to writes, if you've ever seen your writes get slow, is indexes. And indexes are basically trees. They're tree structures. And as the indexes get over a certain size, you see an order of magnitude slowdown in database writes and database performance, just because the index trees are too complicated to recompute in memory, especially if the indexes won't fit in memory anymore, which can happen very, very easily. So this is the most common problem that we see. So what happens is when you're doing index rebuilds and things like that, they get exponentially longer to process because of that single problem. And it doesn't really matter if you're using MySQL or if you're using a document type database or an in-memory database or something that's writing to disk. They all are adding indexes now. The indexes are all the exact same technology that's been around for 25 years. It hasn't really changed at all in that period of time. So everybody is, can experience adverse effects from this. The other thing is you have to watch the life cycle. You don't want to have a database infrastructure that's not backed up regularly. We have also seen that kind of problem where customers had their databases so big that they couldn't take them down in a 24/7 application. So they were operating without backups and hoping that replication was going to be good enough. Sometimes it is, sometimes it isn't. We'll talk about that. Monitoring, application updates. Any of you ever go ahead and actually change your applications and add things to the data model? Happens, right? Happens quite frequently. So you need to be able to do that and deploy seamlessly. And with the cloud, we're moving much more into a 24/7 continuous operation model. We see that more and more in the applications that we deal with. So you have to be able to handle all of this without going down. And it's a real challenge, and it takes a little bit of design up front. So we talked about index structures and what they really do. This is essentially a load curve graph that we did with NODB database. This is an actual NODB database, and we essentially were writing records to the disk. So we wanted to see how the write speeds were affected by index complexity. And what you can see here is when databases slow down, they don't slow down in a nice linear fashion where you could say in a month, I'm going to need to do something about this. What happens is the performance goes pretty much over a cliff one day, and you never exactly know when that is. And we've seen this problem literally throughout my career. I can remember building very, very large applications. I worked on an early application that's still in use today for Fox Television. Actually, in the early 1990s, we built that application, and we had this exact same problem where everything was performing fine, and all of a sudden one table got too big. We didn't have an index to handle it or something like that. It started doing disk scans, and all of a sudden the performance just went out the roof like this. So it's a very, very common problem. So what we see here is, in this particular example, we were able to load about 1 gigabyte in 1 minute, something like that. 3.5 gigs took 12 minutes. 40 gigs on a very complex table with a lot of indexes took 10 days and never finished. So imagine that you had to re-index this database frequently. You'd never be able to do it. That's exactly what happened. So when we talk about database scalability, which we're going to get into next, it's exactly how to solve this particular problem. How do you get around it and how do you solve it? So these challenges, again, apply to all types of databases. It doesn't matter if you're using a traditional database management system like MySQL, Oracle, Postgres. They're all IO bound. You have multi-user lock contention, high availability, lifecycle management. NoSQL databases, including in-memory ones, document databases, caching databases. You have reliability and high availability is a huge concern there, especially if they're in memory. The limits of a single server, you can't have more data on a single server than you can fit for those things. Data dumps to disk, lifecycle management. So it doesn't matter what the technology is, databases are hard to manage, and most importantly, to make your database infrastructure elastic so that it can scale as your application grows is probably the biggest challenge in the cloud that I know of. That's the biggest challenge. Like I said, it's easier to scale every other tier, but the database is really tough. So, and also you run into a lot of application-specific requirements where you can do things in an application that will make your database challenges even more difficult. So you want to be sure that your application, again, is as clean as possible. So from this, we came up with what we lovingly call the laws of databases, which is that small ones are really fast, big ones are really slow, so keep them small. That's the moral of the story. And why is that again? It's mostly because of indexing. That's the main bottleneck that we actually see, is if your index structures are manageable, if the index structures fit into memory, you're going to have potentially 10 to 50 times the performance that you will as soon as you hit that cliff and you run out of disk space. So the answer is that database sharding is the only effective method for basically achieving scale, elasticity, and reliability of management. It doesn't matter what database technology you're doing. And whether people call it database sharding or not, every vendor today that's doing SQL, NoSQL, whatever, and actually has any real scalability story is using database sharding. I'll explain what that is and how it works, but everybody is doing this. Again, they may give it another name, but it's all the same basic technology. So database sharding is horizontally partitioning records across different servers. That's what it is. And so what we're doing is, if you see this example, if we have 4 shards and 4 databases, we're taking a big database, we're breaking it up into 4 smaller databases. That's where the word sharding comes from, which, by the way, we didn't make that word up. It's a Google word if you don't like it, so they formulated it. But basically, you're taking a big database and you're breaking it into smaller pieces, and then you're spreading the data across. Very often using a modulus algorithm or something like that to evenly divide and load balance the rows. So in this case, you can see we're spreading customer information, customer 1, 2, 3, 4, 5, 6, 7, 8, across the different shards. So now what you do is your application goes and reads and writes the data from the shard that the data is in. Very, very simple. All of the NoSQL databases are working this way, document databases are working this way, and we're making it possible to do SQL databases as well, which is a bigger challenge that we'll talk about too. So the key to database sharding is simple: share nothing. If you've read any computer science papers on scalability, you know that any shared component will actually totally kill your performance. So you want to have completely independent database engines that are running, so they're not dependent one on the other. And once you do that, then you can actually just keep scaling and scaling. And that's the key to doing the whole thing. So here's the database sharding architecture. Typically, again, we have an application server tier. We have a client, typically a client driver, something like that, MySQL driver, something in that order. Essentially, the client driver needs to be shard aware, so it needs to know where the different data is in each of the shards. And then it can read and write to each of the different shards seamlessly. And then, of course, you have the databases running on the different shard servers. Now, in some architectures, a proxy is inserted in the middle, where you have middle tier servers that are intercepting the database calls and then routing those to the individual shards. We don't think that's as good of an example and as good of a way to do it. And the reason is now you have something else that can break. It adds to the cost. It adds to what you have to administer. And it's not as fast because you don't have that direct client to database connection. So if we can keep that client connection direct so that you're going straight to the database for reading and writing, you're going to have the same kind of performance, completely scalable, that you're used to in a single environment. So it's a very, very strong way to do it. Here's what it looks like as far as scalability architectures. This is a MySQL application. Again, all inserts, because inserts are the toughest. If you want to measure your scalability and you want to see how your environment works, make sure you're testing writes, because writes are the hard thing. That's always the difficult thing. So in this particular case, you can see that we were able to do about 2,000 writes a second, 2,000 transactions a second on a single shard. We were able to scale all the way up to 10,000 shards a second on 4 shards. So it's completely linear as far as writes go. If you design your architecture right, you can get lucky and actually have better than linear performance on reads. How is that possible? Why? Because things start to fit in memory a lot better, and we're dramatically changing the CPU and memory balance to the size of the database. And you can see, again, multiples of performance on each individual shard. That can show up big time in your application performance. It's really kind of a nice bonus that you get. Something when we first started researching this, we really didn't expect. It was pretty amazing. So why does database sharding work? Again, what we're really doing is we're shifting the balance between memory, CPU, and disk. So if we can make memory and CPU a higher ratio to disk, and then we're minimizing the disk I/O problem that we talked about, and then things work much, much better. It doesn't mean that your entire database has to fit in memory by any means, but what it means is you want at least the indexes to fit there if it's at all possible. If your indexes for a shard can fit in memory, things are going to perform very, very well. As soon as that goes out of memory and the indexes have to swap to disk, it's almost like disk swapping in your operating system when you run out of disk. It's the same kind of problem that you see there. You can, again, reduce the size of the index trees dramatically, and when the index trees are smaller, they get an order of magnitude simpler and easier for the CPU to actually recompute them. So it isn't just like, if you have a 10 gigabyte index versus a 5 gigabyte size index, that can be much more than a 2 times increase. It could be 5 or 10 times as far as performance goes, because the indexes are so simple now. The computation that's involved to insert something in the middle of the index is much, much less work. Again, you don't have contention between servers. This is great for locking. Anybody have locking problems with multi-user, lots of multi-user transactions? Right, where you see that? Well, the reason is that every DBMS only has one lock manager in each instance. So now if you have 4 shards or 8 shards or 16 shards, now you have multiple lock managers. Each one has its own. And so the effective user contention goes way, way down. And that can be very dramatic too. So it also allows for intelligent parallel processing. If you ever have to do aggregation processing on the fly, if you've ever done those kind of queries, you know, where you're doing select count star from whatever table or something like that, or group bys, those involve a lot of sorts, a lot of disk I/O, of reading a lot of records and making those work. And so when you put those together, it can be much, much faster in a sharded environment, again, because you've got so much less on each one. You can actually run those queries across all the shards, bring the results back and roll them up. Can be much, much faster, actually. That's where you can get a better than linear performance improvement. That's one of the most common places we see that. And again, the goal is to keep all the CPUs busy and productive. That's really what we want, is we want to get the money out of our CPUs and really make them work. So this is the family builder graph after they started implementing database sharding. And what you can see here is it's hard to read here, but the dark spot is the actual I/O weight. So the dark line in the middle, and then the blue is all user CPU. So in this particular example, after implementing just 4 shards, we were hoping they would need more shards, by the way, but they only needed 4. They actually now can do as much marketing as they want in the company. They don't have this problem where it crashes anymore, all those kinds of things, so they don't have to go running and complaining to the marketing people. And they actually today sign up as many as 100,000 users, new users every single day. So it's a 24/7 application. They're signing up 100,000 new users a day. It's performing perfectly. Again, the database infrastructure is completely reliable and everything is working fine. So this just gives you an idea of how dramatic it can be from one shard just to 4 shards. So this is not even a huge infrastructure, and it's worked out very, very well. So now let's talk about the different types of databases and what database sharding means for all of those. I know most of you are interested in relational databases. That's my favorite as well, so I'll talk mostly about that. And then we can touch up on the NoSQL databases also. So we all know that the relational databases are very proven. There's no question about that. They use the SQL language, although you can use object relational manager tools to get around that so that you can have it be a more object-oriented approach. They're very durable, transactional, dependable, but they are perceived as inflexible. A big driver, we believe, to all of the NoSQL adoption is we've got a lot of new developers that are looking for a more flexible way to deploy data models. And it's true that with NoSQL, which is the opposite approach, right, you can do that. You can have a much more flexible model. But one thing I'd like to ask is, what good is most data if it's not related to other data? Right? I mean, in other words, all of you are sitting in this room. We're at a conference, so we're part of the conference and related to that, right? We might be working for the same company or different companies. We might have customers that we work with, and we have groups of those. So really, all data is related, right? All data is based on relationships. And early on in the mainframe days, there were very simple database structures that were incredibly high performance that looked an awful lot like NoSQL databases. And the reason that people brought about the relational database and why it was invented in the first place is because people couldn't express those relationships easily and be able to actually model their application that way. So that's really what happened. But it doesn't mean that NoSQL is bad by any means. There are some very, very good use cases for that. If you have a relatively flat, simple data model, we've run into some online gaming customers that have very simple games where really they're just reading and writing pretty much one object per user as they play. There's not a lot of interaction for users. That's not a problem at all. They can be great for that. They're very simple. You can get something up and running quickly. It's easy to manage. But if you have a lot of complex relationships, the problem that you run into is that you start to try and figure out how to create those relationships in a NoSQL environment. And what happens there is you end up replicating a lot of data. Anybody familiar with a product called Redis? Okay. If you look at some of the Redis documentation, you can see what they've had to do to sort of bend Redis to do relationship type work. And they'll say, well, you have a list here that points to that list and a list here that points to that list, and the application has to keep them both in sync. It can be a real nightmare. And one of the worries that we have is, as applications get more complicated, which they all will, if you started out with pure NoSQL and don't understand that, your data model design and what the burden on your application is going to get pretty ugly, 6, 12, 18 months down the road. That's a very, very significant problem. So again, that's really the reason. You also have document databases that are getting very, very popular. This is a great structure to use for, again, something that's relatively flat. Again, if you're logging or just tracking lots and lots of transactions and they're all flat and they pretty much have the same data structure, it can be very, very fast to do this and implement it. It's a very, very good use. But again, all these databases are now adding their own index structures. So they're going to have the same exact bottlenecks that you see in a relational database. And again, they're making it harder and harder to actually do relationships. So one common question I ask is, who ever has to bring back a list of related information in their application? Anybody ever have to bring back more than one row of things that are related? Right. So you don't want to have to go looking throughout multiple servers or multiple shards to find, let's say, a list of orders for a customer. You want those to all be together. We'll talk about how to structure that. So this leads us to two sharding approaches that exist in the world today. One is called black box and one is called relational. And the black box sharding they both utilize a key, a value key. They're almost always use modulus, so they're basically saying, record 1 is in this one, record 2 is in this one, record 3 is in this one, and so on and so forth. So it's very, very common. Black box sharding is very attractive because it's automatic. Everybody likes the approach of this because it is automatic and you don't really have to configure anything. The engine can do it all by itself. So that's really a nice approach. It tries to shard everything evenly across all available servers, but there's really no developer visibility or control. So one of the things you run into is, if you're using a NoSQL database, which is really a key and a value, it's fine, because really in a NoSQL database you can only read and write one row at a time anyway. There's no concept of a transaction. You don't really have the idea of relationships. If you do, you have to build them all yourself anyhow. So it works out fine for that particular kind of thing. But as soon as you get beyond that and you actually have related data, imagine if you had, again, a customer, and a customer has orders, and each of the orders are in a different shard. And you need to show a customer on the screen a list of all their orders, which is a very simple requirement, for an application. I bet you all have something like that. Now you've got to go to multiple servers to actually collect those. We call that the scatter-gather approach. So automatic black box sharding means that the rows are scattered for each table differently, and it's controlled by the engine. And so anytime you want to get related information, it's got to go out to all those places and get it. It can be very, very cumbersome. With relational sharding, this is a completely different approach. What you're doing with relational sharding is it's controlled by the developer. So first of all, it does take a little more expertise and knowledge of your data model and how you want to do things. But basically what you can do is you can select which data you want to shard and which data you don't want to shard. So that's a big factor right there. It gives you, again, explicit developer control and visibility, so you know exactly what you're doing. Anybody ever done index optimization in your application? So relational sharding is really the equivalent of that. You can actually make decisions of how you want to shard things based on what makes sense for your particular application. It's tunable as the database grows, but it's extremely, extremely good if you have sets of data coming back that are related. Because why? We can make sure that we keep all of the related data in the same shard for a given customer, let's say. That's a very, very easy way to do it. So we can get those result sets most of the time, not always, from one shard. And that's the whole game in sharding, is how much can I get from one shard and how little do I have to do across shards? Because if you have to do everything across shards, I can tell you a sharded environment is slower than a regular one. Very, very quickly. So you don't want that. So, and the other key to relational sharding is that it preserves all of the relationships in your application. Anybody do joins? Right. Try and do a join in a NoSQL database, right? You can't. It's not supported at all. So we want to be able to preserve all of that. So how database sharding works for NoSQL is very, very simple. In NoSQL, what do you have? If any of you have used memcache, you've seen this a lot. You have put and you have get. It's very simple. So you're putting with the key and you're getting with the key. Pretty simple to do. Document databases work exactly the same way. So if your application works by reading and writing one object at a time, perfect. It's really easy, because what are you doing? Your application says put, the engine looks at that particular piece of that key. It says, where should I put it? Go get it, right? Go put it there. If I'm getting it, then it does the same thing. It looks at the key and says, all right, here's this key. It's in shard number 3. Go read it from there. That's the easy way to do it. With relational sharding, though, you do have to think about things a little bit more. You have to actually do some planning and analysis up front. It's not very difficult, but it's something that's very, very important. So the way we do it in relational sharding is we actually have 3 kinds of tables in relational sharding. The first one we have, and again the colors didn't work out so well here, but the first one we have is we have the shard root table at the top. And so this is the main table that you want to shard. And below that we have what we call a shard tree. And the shard tree basically in this case has from customer, we go to customer orders and order items. So we want all of that data in the same shard for a certain customer. Another customer might be in a different table, a different shard, I'm sorry, and it would have all of their information in that shard. So that's what we call the shard tree definition. But there's a lot of other tables that are reference tables, like global tables, that you don't want to have to shard. For instance, a country code or something like that. So those are the blue tables, and what we do with those is we want to replicate those to every single shard. Why? So that all the relationships to our shard tree work automatically. We don't have to worry about it. So now if we do joins between any of the sharded tables, or any of the shard and the global tables, we're totally fine. We don't have anything to worry about there. So here's how relational sharding works. Again, we're doing the same kind of thing. If you're looking at a single select or something like that based on a key, we can look at the select statement, we can decide where it is, we go ahead and get it. If we're doing a write transaction, we can do the same kind of thing. This is what a query might look like, and if you see the parts that are in blue, that's the part that you're making the sharding decision on. So you can see if the customer ID equals 1, 2, 3, 4, we know exactly where to go. It's actually pretty simple.